This part will be a bit difficult. We will do renormalization group of turbulent flow, but I am going to take a simple example. Okay, so let's so that was kind of overview of turbulence phenomenology, but now we can do some field theory. Okay. So in fact, the idea is that we had this viscosity, which was L to the 4/3 diffusion coefficient. Can we derive this from field theory? So you see the viscosity is increasing with L. So we had viscosity nu L, which is L to the power 4/3 epsilon 1/3. L is increasing, no? It is similar to what we did for Wilson theory, where my parameter, the mass parameter, okay, R was a parameter which was changing with scale. In fact, we did mass renormalization of 5/4 theory, it was changing with scale, right. So that is what we would like to do here, but it is a non-equilibrium system. So there will be some differences. Okay, so that's let's get started. So I will renormalize the viscosity of not the Navier-Stokes equation, but a simpler model of Navier-Stokes equation called shell model. Okay, the field theory is simpler here. We will do Navier-Stokes later in the next class possibly, and let us start with shell model. Okay. So shell model has fewer variables. One drastic assumption is that we divide this 3D sphere into shells, overlapping shell, well not overlapping, but different the shells like this. So this is shell with radius kn plus delta. Okay. So this is un is a velocity field. So in real flow we will have a lot of Fourier modes, and each Fourier mode has a velocity, right, but in shell model we just give one number un. So instead of k square modes having different values, but I have single way number called un. Okay. Now that is one. Second, this wave number of the shells. So shell radius is basically specifies the of the k, that goes as power law. So kn is k naught b to power n. Okay. So the first radius is k naught. So I can draw this stuff here. K naught. Next is k1, which is b times k naught, b squared k naught, b cube k naught, like this. It is in log space, is linear in log space, but if you look at the real in linear scale, this gap will be bigger. B is greater than 1. Okay, b is greater than 1. So this gap will keep increasing. Okay, so this is called shell model, and we will also make another assumption that this shell so we had interaction, right, u dot grad u, that had interaction up uq p plus q is equal to k. So any p can interact with k, right. So if you have wave number k, then this p can be any size, but in shell model we do not allow that. We say that k n will act only with few modes, in fact 5 modes, okay, 2 in the left and 2 in the right. So I will show you that model now. So this is a model. So d by dt of un. So my Navier-Stokes equation has been greatly simplified. This one, my viscous term is nu bar k n squared. This is a kinematic viscosity. Now look at the nonlinear term. It is, so this k n, okay. So it is interacting with 2 modes to the right, un plus 1, un plus 2. This is n plus 1, n plus 2. The next is 1 to the left and 1 to the right. So 1 to the left and 1 to the right, right. This is 1 to the left, 1 to the right. Third is 2 in the left, n minus 1 and n minus 2. So as I said, these are basically 5 modes that are involved in interaction. I do not, this k un does not interact with shell here, does not interact. Okay. This is called local, which has been proven to be correct, well proven to be valid for Navier-Stokes, especially in 3D. 2D has some issues, but 3D it works. So, now what? Now start doing if you recall Wilson theory, please we got to go back to Wilson theory. So, what did you do in Wilson theory? I want to see what is the viscosity at different scale. So, this nu bar will change. So, my nu bar basically is a at very large n nu bar, but I keep going to the left, means I keep coarse graining, and coarse graining means I remove this variable and see the effect of it. So, my viscosity will increase, then I do it here, I increase. Okay. So, my viscosity keeps increasing with scale. I am going to show you this will happen here in this proof, in this scheme. That is what happens in atmosphere. Atmosphere, the diffusion coefficient is bigger and bigger as you go to higher scales. That is why pollution is spreads at different bigger scales. Okay. So, the idea is to divide this way number. So, I am going to make some in fact, following Wilson, we are not going to do it step by step for all of them. We just focus on Kn in the inertial range. Imagine Kn is the inertial range and see the effect of Kn minus n plus 1 and n plus 2, and assume that when I came here I already have viscosity modified. Viscosity, so I came from here all the way, but I am doing my calculation here in this part. Is that clear? I am not going to do all the steps. So, we are going to see at Kn what is the effect of n plus 1 and n plus 2, and how does it, how is un going to be modified. So, the idea is, okay, so I take one more step back. So, A1, A2, A3 are, there is a constraint that A1 plus A2 plus A3 is 1, and there is one more constraint which we will ignore, but the coefficient we choose for our work is this. A1, A2, A3 is this. What happened? Oh, 0, 0, 0, 0, 0, 0, 0, 0, sorry, 0, yes. The sum is 0, sum is 0. Okay. So, let us look at turbulent case in the inertial range. Okay. So, this one intermediate slide. So, it turns out for shell model which is mimicking Navier-Stokes, mod un squared. So, this is not the spectrum, right? Spectrum is mod un squared by Kn. So, remember Ek is un squared divided by K. So, un, so this is 5/3. So, Cn will be K minus 2/3. I take this Kn and multiply there. So, Cn is K to the power 2/3. Epsilon is the dissipation rate, 2/3, and Coulomb constant, and the energy flux is constant, and this has been verified by many simulation. Once a simulation is here, you can look at this is a spectrum which is multiplied by K 2/3, and there are 2 runs, but ignore the 2 runs, the red line. So, the spectrum is K 2/3, K minus 2/3 is constant because I multiply this by K 2/3. So, this becomes 1, right, and the flux is constant. Okay. This is a property of shell model, and it is also seen in Navier-Stokes equation. So, this is a non-equilibrium solution which I am trying to show you that okay, this indeed happens in shell model as well. Equilibrium case, the flux is 0, and the every mode has equal energy. So, it is not power law minus 2/3, but it is constant, and this is the inside is the thing. So, the Cn is constant and the flux is 0. Okay. So, this is the equilibrium scenario. Okay, now let us get to Rg. So, I will start the renormalization group is okay. You can take a small break. Shell model is clear to everyone? Okay. So, let us now, so it is not, well, I mean, okay, it will take 15 minutes to get there, but there are some details in between. Rg analysis. So, this is the equation I wrote right before. There is one thing I am not focusing on, there are some are complex conjugate, some are not, okay, and this is called Sabra cell model. Okay. This is a it has some advantages, but we will not get through that part. Now we are going to divide these shells into less shells and greater shells. Okay. So, this is my Kn, this is the my lamp post, or this is my marker. So, there are two modes, two shells to the right of Kn. I denote them by greater, and the shells to the left, which is denoted by less. So, my idea is, right now I have n plus 2 shells. Okay. Now, what I want to do is, I want to average over these two shells. This is called coarse graining, right? We did coarse graining for Wilson theory. So, coarse grain means I am going to average over, assume that un plus 1 and un plus 2 are random variables with 0 mean, and look at the effect of this averaging or coarse graining into viscosity, this object. Will it increase or decrease, or won't change? That is the idea. Okay. So, we are going to divide some shells to greater and some to less. So, which are the un plus 1 is greater, right? This is the greater. Un plus 2 is also greater, this is greater. Here 1 is greater and 1 is less. This is a typo, this should be less, and this is greater, right? N minus 1 is less, greater, and n minus 1 and n minus 2 both are less. So, we do this coarse graining. So, coarse graining, if you recall Wilson theory, that we average, assume that these modes here are random, and we average over them. So, of course, random, if a single variable un greater or un plus 1 greater, this will give you 0. But what about un plus 1 greater, un plus 1 greater star, what will that be? Not 0. X and X star complex conjugate is not 0. So, it is in fact it is a spectrum. Okay. So, we have these kind of quantities got mixed up. So, I am going to do some reshuffling. So, let us do the averaging now. Okay. So, this is called coarse graining. So, we do coarse grain of this equation. So, this is a average symbol, no, I mean this is normal in StatMech, but coarse graining is applicable only to the modes, greater modes, not to the less modes. Less modes things should remain as is. You do not coarse grain the less modes, so they will remain as is. So, what happens to this? This will remain as is, so remain as is. What happens to this? Less remain as is. So, that is remain. So, I take it to the left hand side, there is a minus here and the minus here, this becomes plus. I take it to the left hand side, and this is the term minus a3 kn minus 2, this one. Now, what happens to this term if I do average? So, 1 is less, 1 is greater. So, what happens to that? So, less guys are not to be coarse grained. So, they will come out of this. So, we have un minus 1 star, un plus 1 greater. So, this will come out, okay, un minus 1 star, un plus 1 greater, and what is this? 0. So, this is 0, this term goes to 0. What about this term? 2 greater, both are greater. So, multiply 2 random, there is no guarantee it will become 0. Okay. Had it been Gaussian, then it will be 0, but Gaussian, right, I mean Gaussian variable x and y, this is 0 unless x equal to y, okay, but there is no guarantee this is Gaussian. Okay. So, we will not assume any Gaussian approximation. So, this one is, we need to compute this. So, I am sorry this got mixed up here. So, it is minus I a1 kn equal to, so I retain it in the right hand side, un plus 1 greater complex conjugate and un plus 2. So, my equation in the left is this, equation in the right, this object, right object. I will compute and show you that this object is some delta nu minus kn squared un less. The right hand side is appears like that. This will be of this form. So, what will it do? I can take it to the left hand side, and what is going to happen is nu. So, left hand side one term is nu kn squared un less. So, bring it to the left. So, plus delta nu kn squared un less. So, these two can get added up, right, and delta nu I know is positive. So, it turns out my new viscosity is bigger. Okay. So, that is how viscosity is getting enhanced. So, it is the effect of this coarse graining. This is precisely what we did in Wilson theory. Okay. There was no d by dt term there, but the idea remains the same. Okay. So, our idea would be to compute this right hand side, okay, and that computation is what we will do now. So, I am sorry, well, this is the same equation. So, we write this in terms of Feynman diagram. So, this minus I A1 Kn, this guy, okay. So, this equal this bit of transport from keynote to PPT, that was happened. So, minus I K1, this is the vortex, this vortex, okay. Un plus 1 star, this is Un plus 1 star, and Un plus 2 greater. So, these two are greater. Now, I am going to do, I am going to, well, right now I do not know what that thing is, but I will do expand it in terms of Green's function. Okay. So, Un plus 2 I write as, so this we done it before, no? The Green's function is again coming into play. So, you can write down this equation, well actually you should write down the original shell model. So, let me just I think I have it in my next slide. So, basically this is the Green's function inverse. So, the viscosity for nu greater n plus 2 will be nu n plus 2, nu n plus 2. Okay. So, I am going to say that viscosity at scale Kn is nu n, at scale Kn plus 1 is nu n plus 1, scale nu n plus 2 is nu n plus 2. Viscosity is not same at all the scales, they are different, and at this scale is nu n plus 2, k n plus 2 whole squared u n plus 2 greater, okay, and the right hand side will have those three terms, 2 in the right, 2 in the left, and 1 in the left, 1 in the right. So, how will I write down equation for un plus 2 greater? So, this is a Green's function inverse, this is a time t, this is a time t. So, this is time t. So, we write this integral g n plus 2 t minus t prime RHS at t prime dt prime, it is going from 0 to t. So, this is the definition of Green's function, and using Green's function I derive the solution, right. I mean this is we did in the one of the first few classes. So, this is what you get here, nu n plus 2, this one Green's function, and the vortex for the Green's function. So, there is a vortex, RHS will have vortex in front, but there are 3 terms, but it turns out the one term which is non-zero will be the 3 terms here. So, here what is the, so in fact it is good to write in diagram, okay. This is the beauty of Feynman diagram, we do not need to write down all the terms. So, this is, remember this was u n plus 1 star, this is u n plus 1 star, right. So, what should come from the left so that I get a non-zero value? If it is Gaussian, right now we will assume that if it is u n plus 2, then it will be 0. So, u n plus 1, u n plus 2 average is 0. It is similar to what we have uk prime average is 0 unless k prime equal to minus k. If you have same mode, then you get non-zero value, or otherwise you have 2 random variable x y, average is 0. If 0 mean they are random, they will be 0. Okay. So, this has to be un plus 1. Okay. Now, you can see that un plus 2, one term is un plus 1. So, what should be the other term? RHS has 3 terms, the one which will non-zero will be un plus 1 and un, and the vortex is I3 kn. Okay. So, this is the term vortex here I3 kn, one term un plus 1 and it goes with complex conjugate. So, that will give me a correlation function Tn plus 1 t. So, this is a time t and this is a time t prime. Remember, this is a time t prime. So, these are bookkeeping, you have to just do it carefully and then you get it right. So, this is the time t, the t prime, that is why I have t minus t prime. Time is stationary, if I shift the origin it does not matter, but it is depends only on the difference in time. So, that is the correlation function n plus 1 t minus t prime. I put a bar here for reasons which I am going to show you in a minute, and this is un less t, which is same as this term. Okay. So, this diagram, this part of the diagram, this one is a number, is in fact is integral, well not integral here, it is just a number. This is going to correct this new bar, this new bar. Okay. This is one term, but there is another term which is I can expand this using Green's function, right. I mean, why only expand the bottom one, you can expand the right one as well. So, this is a Green's function which is n plus 1, and you do the same kind of stuff, then you get a correlation function below and is again un less than t. So, these two diagrams, this called this is self energy, this is called self energy. Okay. This is the name from particle physics and field theory, self energy diagram, and these are going to make corrections. Now, our objective is to compute this diagram, that is it, and we got the correction. Okay. So, let us do it now. Next slide I am going to do this algebra. I am sorry, this is 0, okay, not 0 to t. So, we got so there are 3 terms, but the non-zero, the term which will give non-zero value are only this. Actually, there are some more. I will send you my paper, okay, where I wrote all this. So, un plus 2, the term in the right hand side will be un plus 3, un plus 4. The ending is 0, right, because I am keeping only un plus 1 and un plus 2. So, there are simple logic to rule out the other 2 terms, and only term survives is this. Okay. Now, RHS, which is minus I A1 k. So, this is the Feynman diagram I wrote, n plus 1, n plus 2. I am going to substitute this un plus 2 here. Is that clear? These RHS of the equation which I wrote in my previous slide, and this is going to make some correction to nu bar. Okay, that is what I am looking at. So, un plus 2 I just substitute. So, this part is, you can see un plus 2 is here, I A3 kn is here, A3, the A1 is here, but I and minus I will give you 1, right. So, this is become 1. So, A3 A1 is here, kn and kn will be kn squared, this un less which is here, and un plus 2 and un plus 1, right. So, this un plus 1 which combines with this un plus 1 star. So, I got this, but this is t and t prime, please note is t and t prime, 2 different times, and this guy is also t prime. So, there is a bit of problem. I want un of t, right, my equation in the previous slide is un of t, but this guy is un t prime. Problem, no, because I want at time t and I have this integral inside and I need to integrate this stuff. So, what should I do? So, I make an approximation, okay, this is called Markovian approximation. Okay. So, Markovian approximation says that this integral gets maximum contribution near t equal to t prime. So, this t prime is from 0 to t, but it gets maximum contribution when t prime is close to the upper limit. So, I have integral 0 to t e to power minus, so let us imagine that I have e to power minus T alpha dt. So, under what condition of alpha I will get maximum contribution for T in the upper limit. Okay. You can easily argue when alpha is large, then you can get maximum contribution when T prime is close to T. Alpha should be large, and this is called Markovian approximation. Okay. So, this approximation is made, then this guy comes out as a T. Okay. So, basically we can integrate this minus alpha T. Okay. So, you need to do plotting and so on, you can convince yourself that this is happens when alpha is large. If alpha is small, then all of them will contribute. If alpha is large, then it turns out actually it is so it drops suddenly near T, and that is where big contribution comes from here. It requires a bit of plotting and you get that. So, this U n T prime becomes U n T. This is a critical approximation. It is called Markovian approximation, which is made, and then we get okay. So, this guy will come out. Now, I am left with these two Green's functions, sorry, Green's function and correlation function. Now, I need to do the integral, otherwise I can't get a number, and these are some funny functions, right. I mean, I do not know what they are. Well, pretty hopefully we can simplify it, but it's a I do not know what the function is. So, we came other approximation that this Green's function is exponential minus nu k n square T minus T prime. So, this nu n is a renormalized viscosity or viscosity at k n. So, nu n k n squared T minus T prime, this is the Green's function, and correlation function T bar, the time dependence is exactly same as this, nu k n square T minus T prime. You can easily check that nu n k n squared is dimension of time inverse. Okay. And this C n is the equal time correlation. This is 5/3 or this is minus 2/3. This is the Kolmogorov spectrum, this guy. Okay. I plug it in. Now it is easy, no? I mean, this integral are basically exponential, I can easily integrate them, right. The two exponential, in fact, they get added up. Okay. So, these are critical assumptions of RG, and once I put that, then I get this. So, the integral, you see there are two exponentials, I can easily integrate them and that comes in the bottom. So, my integral of the first diagram, there are two Feynman diagrams, the first diagram is this, and this is nicely U n T, and this is, well, I do not know what is C n plus 2 right now, but I will assume, well, I am going to do some assumption again, and I do not know what is nu n plus 1, but I will make some assumptions and I get a number. Okay. Right now I 1 is some function of C n plus 1, C n plus 2 and nu n. Okay. I need to do some more work. Similar procedure can give you I 2, the second Feynman diagram, this second Feynman diagram. Okay. This is C n plus 2. You can look at the Feynman diagram, and this is the correlation of the U n plus 2. Okay. I can add them up and I will get this. So, nu n plus 1 squared is nu bar n squared. So, this I am sending it to the left. I did know, I mean, so this there was plus sign in the left in the previous slide, it became minus sign and I get this. Now, believe me, this quantity is small, nu bar is much small compared to nu n. Okay. So, this guy goes as k minus 4/3. For small k, this will be large number, right, and nu bar is a constant. So, we can ignore this. So, that is where the microscopic kinematic viscosity is not playing much role in atmospheric diffusion, we can ignore it. So, now I need to compute this. So, basically I know what is nu n, but nu n is function of nu n plus 1 and nu n plus 2 and correlation functions. So, this is where a new scheme, well, rather one new idea comes called self consistent closure. So, assume that nu n plus 1 follows something following Kolmogorov theory. So, correlation function I just replace Kolmogorov spectrum, and for nu n I again use dimensional analysis and I write nu n k n squared is nu star Kolmogorov constant square root epsilon 1/3 k n to the 2/3. Okay. Nu n is k n minus 4/3 multiplied by k n squared is k n 2/3. Okay. Substitute it here. In fact, it is pretty funny, you know why I am using k n square root. It will become clear that k n the Kolmogorov constant, sorry, not k n, k Kolmogorov square root, k Kolmogorov will get cancelled. It is easy for to see. There is nu here and there is a nu here, and this nu will become square of square root, and that will cancel from Kolmogorov here. So, Kolmogorov constant gets cancelled, and we get only one variable nu star. Okay. So, there is a nu star coming from here and there is nu star coming from here, this nu star squared. Kolmogorov constant will be 1. So, this together will give you k Kolmogorov, and this also gives you k Kolmogorov, they cancels. Epsilon will also cancel, right. This epsilon 1/3, epsilon 1/3, epsilon 2/3 and epsilon 2/3 here cancels. So, everything is gone. Now, you get nu star squared is just this. It is function of a1, a2, a3 which we know, and b. B is that expansion parameter for the wave numbers. So, I know the nu star. Okay. So, I have computed this viscosity, renormalized viscosity. Okay. Great, no, I mean, this is what is done. So, it will function of b, small b, and b can range from, as I said, it should be greater than 1. So, we took from number from 1.2 to 2, okay, and a1, a2, a3 I already have told you.